Welcome to the asset seminar. So I think Liz is still getting food, so it should be here. It's a pleasure to welcome Joe Deshmukh from USC. Some of you may remember that Joe was a postdoc here, I guess many years ago, maybe 7 or 8 years ago, and he was here for a couple of years, and then he turned to Toyota, where he actually built a nice group in that common methods for cyber physical systems. But then he joined USC as faculty, and today he's going to tell us how logic can help machine learning.
We'll see. Well, thank you, Raju, for the introduction. So Penn was a wonderful place to be. I learned a lot in the 2 years. And in fact, when I was transitioning from Toyota to USC, the only place where I had my practice job talk was at Penn. And I think it was the worst talk I've ever given in my life. And I got such amazing feedback from everybody at Penn that it was a completely different talk that I ended up giving. I don't think I would have gotten a job with my previous talk. So thanks a lot. So now I have a lot of the same people in the audience. So I'm feeling a little nervous about how this talk is going to be, but we'll see. So I have a very ambitious title here. The marriage of logic and learning. And whenever it comes to marriage, it's always something we feel nervous about, right? So what I want to talk about, if this cooperates, okay, that there is a paradigm shift that has happened in computer science. For those of you, those of the younger member of the audience, this shift may not be this obvious, but even 10 years ago, several things that we take for granted now didn't exist, right? So if you look at the development of AI and machine learning over the years, in 1970s, there was this hypothesis, right? To get to general artificial intelligence or advanced general intelligence, Newell and Simon had this hypothesis, physical symbol systems hypothesis, saying a physical symbol system has the necessary and sufficient means of general intelligent action. So there was kind of this hypothesis that you need to have some symbolic system in order to have intelligence, right? And there was the knowledge principle, which was to perform a task well, you need to know a lot about the system in which you're performing the task, right? All of this happened in the 70s and 80s. And then there were the two famous AI winters where the research in AI started drying down, the funding scenario in AI started dying down. And then I think basically around 2011, 2010, when the whole GPU revolution started, machine learning AI kind of took off, right? There were several things that were happening in the interim. So I think between the late 90s and early 2010s, a lot of fundamental advances were made in using statistics, probability, Bayesian methods to really understand where things do not work and how can we reason about uncertainty. And that kind of got us to 2010, where first AlexNet came out and the ImageNet data set came out. Neural networks started performing really well on images, and it kind of just took off from there, right? So now we are in this new reality where basically anybody in any field that is using a computer, the rule seems to be thou shalt use a neural network, right? And if it doesn't work, then you should add more neurons or add more data, right? Also, we are in this new paradigm where we want more and more of data, and just having more data allows us to do more things. So there's a very clear paradigm shift where we have gone from kind of symbolic logic-based methods to things that are involving statistics, probability, and so on, right? Yeah, so let's maybe take a 5-minute break, please. Yeah. All right, so hopefully people can concentrate on the talk more now. All right, so the question is, with all the fantastic things that have happened with machine learning, have learning-based methods solved everything, right? That's the question. And clearly there are examples where learning-based methods suffer. So the first video is of a Tesla car that completely ignores the fact that there's a concrete barrier in its lane and just crashes into it, right? This one is a more interesting one. So the middle video is actually one of the early experiments using deep RL. So what the autonomous agent was trying to do is it was trying to control this white boat. And you can see these kind of yellow dots at the bottom of the screen. These are kind of the boundaries of a track along which this boat was expected to run. And if you see, there's a map at the bottom, at the top left, where it's showing all the other boats that are running in this race, right? So the goal of the deep RL algorithm was to make the white boat run the course as fast as it can, complete the track, and on the way also get some rewards, right? So the way the reward shaping algorithm, or the way the rewards were defined, was if you see there are these little green things that kind of pop up periodically. You can think of them as cash or gold or whatever. And every time you get close to one of these green things, you get a reward. So there were rewards defined for the boat completing the race, staying within the yellow boundaries, and getting this gold. But what the agent very quickly learned is, you know what, I don't have to stay within this course. I don't have to even finish the race. If I just keep crashing into things, as long as I keep getting close enough to the gold or cash, I'm maximizing my reward, so everything else can kind of go for a toss, right? This is yet another kind of thing where a learning-based method learned something that does maximize some objective, but that's not the right objective, right? And then there are more egregious examples of things like bias or unfairness creeping up into machine learning algorithms. So clearly, learning-based algorithms have some ways to go before we can start using them in things that are safety critical or are fair or unbiased and so on, right? And there's a lot of research happening in this field to kind of bridge the gap between learning-based techniques and kind of symbolic techniques. And many prominent philosophers and computer scientists think that learning and logic should be combined. If you're interested, there are articles, many people have opined about this issue. Several people believe that having some kind of neurosymbolic hybrids will help. And since the middle of the 2010s, there have been some people working on neurosymbolic techniques to kind of bridge the gap between kind of the neural network world and the symbolic world. Right? So what this talk is about is looking at some specific problems in this hypothesized marriage between logic and learning, right? So just to put into context what I'm specifically going to target is that logic-based methods bring all these set of techniques, right? So for example, you can reason about or express causal or temporal or ontological or even epistemic relations about data. Whereas in learning-based methods, you are primarily interested in statistical relations, correlations, and so on. Of course, there is work on causal learning and using causality in the process of learning as well. But that's a rather newer thing that's still emerging, right? In logic-based methods, we think about specifications, safety constraints, task objectives, which are again kind of formally defined. Whereas in the machine learning world, it's a data-driven world, right? Where we look at labeled data sets. It's essentially all the information we can gather from data. In the logic-based world, we are very excited by proofs and guarantees and building assurance cases. Whereas in the machine learning world, there are things similar to that that are about giving performance guarantees, getting error bounds, regret bounds. So there are kind of formal guarantees that also exist in that world. In logic-based methods, a common criticism is that the methods have high theoretical complexity, things don't scale. And in machine learning, there is also the problem of being data hungry. Your sample complexity might be very high, so you may not be able to learn effectively. In logic-based methods, we are, I think really, if one were to capture the essence of logic-based methods, it's about symbolic reasoning. Whereas in machine learning-based methods, there's more of a kind of a neural or kernelized learning that is what makes it very powerful, right? And the general perception is that these methods are cool, fancy, but they don't really scale. They work on toy examples. Whereas, of course, these are perceived as highly scalable, right? And we know that they're highly scalable. They can do things that humans have not been able to do, and they can go to kind of the next level, right? So question is, how can there be a marriage between these two very different worlds. Okay. So hopefully the marriage doesn't end like this. So specifically, the questions I want to look at in this talk are, can we use logic-based methods to improve learning-based techniques? Okay. And secondly, can we use learning-based methods to assist in solving problems framed using logic? Okay. And at the intersection of these, there are several interesting topics. I'm going to focus on the first two topics here. Okay. So synthesizing safer controllers for autonomous systems. I'm going to talk a little bit about that. And I had a funnier thing that instead of dominant use of logic-based reasoning, I wanted to say in the first topic, it's logic who's wearing pants in the relationship. But I don't know if that's appropriate to say anymore. But so it's basically more of logic, right? And topic two is kind of statistical methods to use in the context of verification. And here, it's really the statistics machine learning methods that are the dominant ones. And we want to kind of get at logical reasoning here. So other areas we have worked on in this attempted union that I won't talk about today are things related to time series learning in various settings. So here you could learn logic-based formulas from data. We have been working on a new language called shape expressions, which are like regular expressions, but atomic units are instead shapes. So they can help you express interesting behavior in time series data. We have been looking at some human AI interaction using kind of epistemic models of trust. We have some work on doing robustness of neural networks. That's a very new work, still not published. We are also doing some work on learning kind of information from network flow data. So there are several places where both machine learning and formal methods have a space, and combining them could allow us to get some new insights, some new algorithms, which are more explainable, perhaps come with more guarantees and so on. Okay, but for the purpose of this talk, I want to focus on these two topics, synthesizing safer controllers for autonomous systems. And then later, I'll talk a little bit about statistical or deterministic verification. Okay. So just to kind of set the tones, just make sure everybody's on the same page, how do we typically model dynamics and control for autonomous systems? So as you know, autonomous systems are systems which have some physical component being controlled by software. And these systems typically operate in highly uncertain regimes. And one of the approaches to model them is using either non-deterministic or stochastic dynamics. So in the non-deterministic case, we assume that given a state at some time n and some action at time n, the next state is in some set that is defined by this function f, the dynamics function. In the stochastic case, we might model given a state at time n and the action at time n, there's some distribution over where the next states may lie, right? And if we want to design a deterministic controller, then it's some function that maps your current state to the action. And maybe this controller could be parameterized by some set of parameters. So for example, if you design a PID controller, your parameters could be the gains of the proportional integral derivative parts. If you are using a neural network, then your parameters could be the weights and biases of the neurons and so on, right? And typically, irrespective of which method you're using, there is a notion of a trajectory, right? So the trajectory is typically a sequence of states that satisfy the system dynamics. So in case of the deterministic systems, it's going to be a sequence of states that's consistent with this relation. In case of stochastic systems, the stochastic systems will induce a distribution over the space of trajectories. And a trajectory that we look at is going to be some realization of this kind of stochastic process defined by this distribution, right? You can also look at stochastic control policies, where your policy function is not a function from states to actions, but instead it's a distribution over the space of actions conditioned on the current state and the parameters of your control, right? So, so that's how we typically model either non-deterministic or stochastic models for autonomous systems. And the control problem for, I'm going to make two different cases, control problem for deterministic or non-deterministic systems, where what we are given is we are given some set of initial states for the system. we are given some performance function that maps trajectories to some real value, and we are given some safety constraint, phi safe. Now, traditionally, it's convenient to think of the safety constraint as a Boolean function that's going to say, am I safe or am I not safe? You can also do that, but I think it's easier to present if I just say that my safety constraint is also going to give me a real number. If this number is positive, then I'm safe. If it's negative, I'm not safe. And the magnitude of this number kind of indicates how safe or unsafe I am. Okay. So one of the control problems that we find interesting is how can we maximize performance of your autonomous system while guaranteeing some safety margin? Okay, so we want to find the set of parameters theta of your control policy that maximize your performance function while ensure that you're at least rho safe, some rho margin away from unsafety. Or you could also maximize safety while guaranteeing some minimum level of performance, right? Where we are saying, ensure that my phi safe specification holds. And in fact, we would also be interested in checking that the theta that maximizes this phi safe, the value of phi safe is positive, not just the maximum, because the maximum value could be negative. That would be bad. We want it to be positive. But we also want to make sure that the performance that we get is at least above some threshold. Okay? So this is a very general formulation for the non-deterministic case. For the stochastic case, there's a very similar formulation, except that because it's a stochastic system, our space of trajectories is not a set, but it's a distribution. So we cannot give absolute guarantees, right? Because of the uncertainty in the dynamics, because of probabilities, no matter what controller you choose, there's always some probability that bad things are going to happen, right? So here, we are still interested in maximizing the performance metric, but we want to make sure that the probability that a random trajectory is safe should be greater than some user-provided threshold. Or similarly, we may want to maximize safety. So we want to maximize the probability of being safe while ensure that the performance is above some threshold. Okay? So very similar looking problems. Question is, how do we solve them, right? So one of the first things I would like to go into a little bit is, I have been talking about the safety constraints or performance specifications very generally. Let me talk a little bit about specific examples of how we can express phi safe. And here we are going to use everyone's favorite logic. I mean, this is a bit of an inside joke, but STL is a logic that my group has been using, and several other groups have now started embracing it as one of the logics that helps us be very flexible in the kind of requirements we can specify. So we are going to talk about a little bit, I'm going to give you a little bit information about what STL looks like. And then I'm going to look at some other challenges. Okay? So signal temporal logic is a logical formalism that you interpret over time series data or temporal signals. So here's an example of a very simple STL formula. This says that always between time 0 and 100, the value of the signal x at all times remains between 1 and 3. Okay, so it's just specifying some bounds on this signal x. A slightly more interesting formula, it says that eventually between time 20 and 60, it's always the case, there is some time such that from that time on, it's always the case that the absolute value of x remains less than 0.1. So if you are a control theory person, you can see that this is kind of specifying the bounds on settling time for this signal with the settling region 0.1. Now, these are more kind of control theory inspired examples. We have other examples where you can specify task specifications for a robot saying, go to this room, pick up this item, then go to that other room and come back to your original room within some time period, right? Or we can have examples in autonomous driving where we specify various margins between you and the car in front of you, you and the car next to you, and complex temporal specifications about the relations between these things. I have some slides which I can show you offline if you're interested to see. But STL is a very flexible logic that applies in various domains. It's been used in automotive extensively, in healthcare. Many different areas have made use of this logic. And there has been a lot of work in the robotics as well as the cyber physical systems community on using STL for various things. One very good thing about STL, so actually there's a cousin of STL called metric temporal logic, and this work actually started right here in Penn in George Papas's group. So Yorgos Fanikos came up with this idea of quantitative semantics for these temporal logics. And I think this is the really cool thing about STL is when you think about a logical formula, typically you think about, do I satisfy this or do I not satisfy this? So it's a very Boolean thing. In STL, you can also come up with how well do I satisfy the formula, right? So here's an STL formula that says always between time 50 and 100, the value of X is always less than 3. Now, clearly, this signal does not satisfy the formula because there's no time when this value of the signal is less than 3. Here, the quantitative semantics of STL will return to us this thing called an approximate robustness degree, which will quantify how bad is the violation. Whereas this signal does satisfy the formula. Here, it's going to give us some estimate of how far am I from the bad set. Okay? And this is going to be a signed distance. So if it's positive, it means you satisfy the formula. If it's negative, it means you do not satisfy the formula. Okay? So with this background of STL, I think we are ready to take on the next challenge, which is everything I have told you about control synthesis. Control theory is an area that is as old as the hills, right? I mean, people have been working on it for a very long time. Many things have been done. So what's new? I think yes, please. Good question. There is actually a zoo of quantitative semantics for STL now. There are the very formal quantitative semantics, which are in terms of distances to sets, which are not always efficiently computable. So there are all kinds of approximations that people have come up with. And they all kind of reflect the same philosophy that if I'm positive, I satisfy, if I'm negative, I don't. But then there are all kinds of choices. So for example, some people look at, on an average, how well do I satisfy the formula? Or there are all kinds of semi-ring structures you can impose with which you can compute different interpretations of what it means to satisfy something. We can talk more offline, but yes, for now, we just choose like one of the most basic traditional quantitative semantics. But I think most of the work I'm going to present doesn't really matter which semantics you choose as long as you've chosen something. Okay, any other questions? All right, so the next challenge is that in the control synthesis problem that I presented, I was kind of assuming that you know your dynamics function or you know the probability distribution on states. But one of the biggest challenges today is it's really difficult in real world systems to sit down and write the dynamics or sit down and figure out what's the probability distribution, right? Most of the times this dynamics function or the probability distribution on states may be unknown. So what can we do if it's unknown? How can we do control synthesis? So I'm going to present two different methods that we have been looking at. One is kind of based on model learning. Also, you can think of it as data-driven control, where first you use your simulations to learn a model that represents, to learn the f or p function. And then based on that, you can design a controller. So I'm going to call this neurosymbolic controller synthesis, where we learn a neural network representation of your dynamics and then try to synthesize a controller. Later, I'm going to talk about some methods where your p function is unknown. So you basically have some underlying Markov decision process which you don't know, and then can we use machine learning techniques like reinforcement learning to learn a control policy. But I'm going to talk first about the neurosymbolic controllers. Yes, it's going to be independent. Yeah. All right. So here, what I'm going to assume is that you have some neural network representation of your dynamics. So given a state at some time n and some action at time n, it's going to predict what's going to be the next state. And let's say you have this neural network representation. We are going to assume that the controller is also a neural network. Okay, so the plant is a neural network with some parameters w. The controller is some neural network with some parameters theta, right? So the control policy is parameterized. We are going to assume that your STL specification phi safe can be translated to a control barrier function. I'm not going to go into details of what a control barrier function is, but you can think of it as a function very similar to quantitative semantics that's going to evaluate to positive if the trajectory satisfies the formula, negative if it doesn't. Okay, so we translate this STL specification to this STL CBF. And then we have an algorithm that tries to optimize your performance specification while ensuring that the validity of the CBF conditions are met. Okay. So this is the general idea. It might sound like a very brute force idea, because basically what we are doing is we are unrolling the plant dynamics over a given trajectory length. We assume that the STL formula is also over this bounded horizon, and we take the state and the action as predicted by the neural network controller, predict the next state, then take again the action predicted for that state, take the next state, and so on. Yeah. Could you say that again? So we can translate all of STL that has bounded time horizon specifications. So we have a procedure to automatically take any STL formula. For convenience, we assume that the STL formula is in NNF, negation normal form. So all the negations are on the predicates. But beyond that, it doesn't really matter, because there are theorems that show that you can convert arbitrary bounded horizon STL formulas into NNF. So it's not a restriction. Yes. So I'm going to tell a little bit about how we do that in just a second. Yeah. Yes. Excellent question. And this is going to be the elephant in the room for the next few slides, and then hopefully we can drive the elephant away. Okay. But for now, I'm just going to leave your question as great question. Let's come back to it. Okay. So a few things, right? First of all, what's the high level approach? We have these decision variables that are controller parameters. I guess I didn't talk about this, but I think I have a backup slide on how we compute the STL CBF. But basically, if you know about let me tell you a little bit in a nutshell how quantitative semantics of STL work. So first of all, STL formulas, the atomic parts are signal predicates, which are things of the form f of x greater than 0. So for atomic predicates, we come up with a function that evaluates to positive if the predicate holds and evaluates to negative if it doesn't hold. Okay, pretty straightforward. For conjunctions, we basically do a smooth min. So you can replace conjunction of two things with a smooth min of the individual functions. For disjunctions, we can also just use, so for example, Rahul Mangaram's group here had a version of STL called smooth operator, where they replaced basically max by just doing the min over the negated things. We have a slightly different way of doing that. We compute a weighted average. So I don't know if there's a pen here. Oh, I guess. So if we have a CBF for formula phi1 and CBF for formula, let's call this CBF1, formula for CBF phi2, then for phi1 and phi2, phi1 or phi2, we are going to come up with a CBF, which is going to look like summation beta I CBF of I divided by summation beta I squared CBF divided by summation of beta I squared. I mean, the squared just ensures that those parameters are positively affecting the CBF, but it's basically a weighted average. And then you can show that if the weighted average is positive, then the disjunction holds. Okay. What's interesting is in the smooth max operation, there's a parameter that kind of controls how conservative your smooth max is relative to your actual max. Similarly, in the weighted average, you have these parameters that control how close your approximation of the max is to the actual max. And what we do is we also include these smoothing parameters as decision variables in our optimization. Okay, so we optimize over all the controller parameters and the smoothing parameters. And then at a high level, we are basically going to do some flavor of stochastic gradient descent. We ended up using Adam because that a variant of Adam because that's the one that worked the best for us. Adam, for those of you who haven't heard of it, is adaptive moment estimation. It's kind of the thing everybody seems to like in the machine learning world. Pratik might have some opinions about it that I'm interested to hear. But we basically compute gradients with respect to both the STL-CBF and your performance objective. And then we speculatively update the parameters and see, is my safety constraint going to get violated? If yes, then I'm going to pick an update that kind of tries to make me safer. If it's not going to get violated, then I'm going to pick an update that makes my performance better. Okay, so there are more technical details in the paper about how we do this, but that's roughly the main idea, right? You either want to make your system safer if it's not safe, and if it's safe, you want to improve the performance. Okay, so these parameters, this kind of iterative procedure, alternating procedure of alternating between performance and safety, has sort of the effect that we get using Lagrange multipliers. So you could also just enforce your fee-safe constraint as a constraint on your constraint optimization using Lagrange multipliers. But we found in experiments it doesn't work that well because our cost function, objective function, is highly non-convex, and there are several things that it needs to work well that don't really work well. So this iterative procedure seems to have the same effect, but it works slightly better. Again, this is a very high-level talk, so I'm omitting several details. If you're interested, I can talk offline. So how does it work, right? So here are some results on a highly nonlinear. This is a 6-dimensional quadcopter example. This is a highly nonlinear 3-dimensional system. In the first one, I is the set of initial conditions. The STL specification is you must be in one of these blue balls within some time period, and you should never enter the red ball. And the performance specification is get as close as possible to this star. Okay. So these are, this is again another example. Here the specification is you must get to this region P3, but you should not be in either P1 or P2. Yeah. No, the model here is, so the plant model is just given the current state and the action, what's the next state? By task dependent, what I mean to say is which STL specification we want it to satisfy doesn't appear in the training part. Those are completely decoupled. Okay, it's just if my quadcopter is here, if I push it here, where will it go? If I push it here, where will it go? That's the training. And then once we have it trained to our level of satisfaction, then we use it in this. So, I mean, I just showed you some fancy, nice looking plots. How much time did it take to get those plots? Were they good? And so on. So for example, off the top of my head, for this particular learning problem, it took us something like 155 seconds with 10,000 iterations. It was a 6D example, fast enough to simulate. So and the number of parameters that we were tuning over were to the tune of 150 parameters, right? So for the real machine learning people in this crowd, they would be laughing internally, like, oh yeah, 150 parameters, yeah, great, right? But the point is, with 150 parameters in less than 3 minutes, we can learn a controller that comes with some guarantees, right? So now if you want to go after a real system and you want to have 1 million parameters, it's conceivable that we could do this, right? With the right setup, with the right performance cluster, high performance cluster, we could do it. It's possible. This is just to show the feasibility that it can be done. Okay, similarly there, I think something like 10,000 iterations, we are able to learn a controller that works well. Excellent question. I will get to this in part 2 of the talk on how we give guarantees. Okay, so So just some observations at this point. This method that we have scales reasonably well with trajectory length. So for example, in this case, the trajectory had 50 time steps. So if you assume that time steps are at even half a second, 25 seconds into the future is reasonable. Here we had 100 time steps. It still scales with the trajectory length. It scales reasonably well with STL formula complexity. We have a paper recently accepted to ICCPS where we consider a long STL formula with several nested eventualities, where we are kind of trying to show some practical version of exponential stability. We are able to design controllers that guarantee that. Okay. It will definitely suffer as the state dimension increases, because then your width of the neural networks increases, number of parameters increase, your optimization problems become harder and harder. So if you want to use continuous states, images as states, I don't think the technology is quite mature enough to try it on that yet, but it's conceivable that we can do something, right? And if the trajectory length increases a lot, if your STL formula horizon is a lot, things will start going up. Okay, I'm going to talk about the guarantees, and I'm still going to keep your elephant intact, right? One possible way to give guarantees for learning the neural network dynamics could be, so I was talking to Nikolai earlier, and I think some of the techniques from statistical learning theory could help us bound on how much error there can be between the neural network that you learn and the actual dynamics. So you could come up with packed bounds, and then you can give probabilistic guarantees on the whole thing. Okay, so that's something that we can explore in the future. We have some other ways of doing this now that I'm going to talk about also. Okay, let me breeze through the second part of this. So far I have talked about how do you learn controllers if your plant model is a dynamical system, controller is a neural network. Now I'm going to talk about the setting where you have a simulator, for example, and your underlying model is some kind of an MDP, and you have some formal specification. Okay, so all of you have seen this picture at some point, I'm sure by now. So in RL, you typically have an autonomous agent that's interacting with an environment. It takes some action. The environment tells it what's the next state, and it also gives it a reward, right? And most current RL or deep RL methods use some kind of state-based rewards. The high-level problem we are trying to understand is how can we use an RL or deep RL method to in an existing RL deep RL method, but we want to make it satisfy some high-level specification. So how do we engineer rewards that make the RL method go towards a policy that satisfies the specification or maximizes the probability of satisfaction of the specification? Okay, one of the biggest challenge that comes with temporal logic specs is that they induce non-Markovianity. So let me tell you what I mean by that. So consider an autonomous agent moving on a number line. It starts at the origin, and this is the temporal logic spec that we want it to satisfy. Eventually, between 0 and 5 seconds, go to the left of the point -1, and within 5 seconds of that, go to the point to the right of +1. Okay, so if you use your traditional RL method, which is going to associate each state of the MDP, which is each state of the number line with an action, what action should it take at the origin? Should it go to the left or should it go to the right? Now, this depends on whether it has already gone to the left of this point. If it has, then it should maybe go to the right. But if it hasn't, then it should first go to the left. So if you look at this problem and try to let me just come up with a purely state-based action, then you're not going to succeed, right? So one observation is that you need to somehow incorporate the state of the specification. Where am I in satisfying the specification also as part of your policy? So the world of RL from logical specifications has seen an explosion in the past 5 to 10 years. And there are a lot of papers on this topic. There are some from Rajiv's group, Kishore and Sugman have some work, very interesting work. There are some works that we have done. Kalin Belta's group has done a bunch of work on this topic. But again, the question remains, how do you, given an LTL, STL, or MTL specification, how do you generate rewards that kind of guide your policy towards satisfying this specification? So the main idea is we abandon the idea of doing this on the original space, but we now work in the product space, where the space is the product of the original MDP and the state space of the specification. And some of the ideas that have been explored in this community are converting the satisfaction of a temporal logic spec into a 0-1 reward. So you run a simulation. In that particular run, if you satisfy the specification, you get a reward of 1, otherwise you get a reward of 0. And then if you want to have infinite horizon specifications, there are some special considerations that have to be done to make sure that even in the infinite horizon behavior, you satisfy the spec. Other things people have tried is converting temporal logic specs into mixed integer linear programs and solving training using basically optimization. In Rajiv's group, there's work on breaking a specification into several sequential sub-goals and then training an RL agent to satisfy each sub-goal kind of sequentially. And there is some work from Cullen's group and our group where we have tried to use the robustness semantics or the quantitative semantics of the temporal logic to kind of guide the RL policy, right, as a reward signal. So here's one of our early works on this topic. So in this is the original 2015 deep RL paper from me and other people. And this is at the 730th or so iteration. I learned something very interesting from my student. Again, borrowing my student's words, I'm not sure if this is the best way to put it, but he said, oh, when we use deep RL, all agents become suicidal. So I said, what do you mean by that? So what happens is, in this particular, the way they have defined a reward is if the agent is between +12 or -12 degrees, and if the value of the displacement is between ± 2 units, then it gets a reward of 1, otherwise it gets a reward of -10. So initially, while the controllers are still learning everything, all the controllers are kind of crappy, the pole is kind of following all over. The only feedback it gets from the environment is you suck, you suck, you suck, right? And the controller, the agent basically figures out that, you know what, if I end my episode, I do get some terminal penalty, but that one terminal penalty is better than trying to stay alive and getting this constant criticism. Okay, very real world, unfortunate. Hopefully none of you have ever experienced anything like that, but you know, this is what happens. Whereas if you use temporal logic robustness as a guidance, what happens is you keep getting all these intermediate results, which is kind of like, yeah, you're fine, you're getting there. Yeah, you're almost there. Keep going, keep going. And it somehow helps the agent to learn a policy that's much better in less than half the number of iterations, right? Yeah. So in this case, we are using a dense reward function because basically the way in this paper it works is we do a rollout, we compute what's the robustness of the rollout, and use that as the reward signal. So on these 8-step rollouts, we get dense rewards, right? So we are not going to get just 0-1 rewards. We are not going to get sparse. Yeah.
Different like trajectories that can see the behavior that we want. Like you can either go left and then right, or then you can go right. And either one of those will give you the optimal result.
So in this example,
yeah, that relation, like there are two possible.
Here in this one, no, I mean, you have to go left first. Otherwise, I mean, you could go right and then left and then right. That would work. But within 5 seconds, you should be here. And with that, you should be here.
I mean, like, I just wonder, like, why RL cannot do that. Like, is this just a problem with that? Because, like, as long as the exploration is good enough to get, like, one trajectory that goes first off and then right. And the other example is logic collection, it should be able to go other.
So if you do it in a very Monte Carlo way where you have the time at which you take action as part of your decision, then it could do that. But if you only base it on my position, so if you have a positional policy, if I'm here, do I go left or right? The answer is, if I'm at the origin, I cannot decide, right? Should I go left or right? At best, I can do something stochastic with some probability I go left, some probability I go right. But no matter what probability distribution I pick, I might, if I pick with 0.9 probability, I go left. Then I come back, I might again with 0.9 probability go back left, and I may not reach right again, right? So if it's only dependent on position, it's not going to work. You have to know what I have accomplished in the past. So it's kind of history dependent. But you can make it Markovian by adding the state of the specification. Then it's, I am at the origin and I've already gone left, so now I should go right. Yes, you can. So that's basically the first step that people do, that do RL over the product space. But then there's the question of, if I end up using sparse rewards, it doesn't work that well. So what we are trying to do is, can we do something better than just sparse rewards? Okay. All right. So after we wrote this paper, we realized that we ended up optimally annoying both the formal methods people and the RL people, right? Because this robustness guided RL was just like it's just a heuristic, right? It doesn't give any guarantees. Is my final train policy going to satisfy my STL spec? I don't know. Maybe it will. And if we then end up using things that do give guarantees, what we found is, because they use sparse rewards, they have terrible convergence rates, training variance is high. The RL people are going to say, this is nonsense. Like, it doesn't work. Why are you using this? Okay. So one of the things that we have been looking at for the past couple of years is in moving away from STL to something a little bit more structured. It has the same expressive power as STL, but it's basically a symbolic automaton. Okay, so the way you read the symbolic automaton is the automaton specification has some state. Okay, and the guards of the or the predicate symbols that appear on the edges of the automaton are conditions that you are going to evaluate on the state of the MDP. So this particular automaton, what it's trying to encode is reach the region labeled D. Okay, and there are two ways you can do that. You can either go through regions labeled A and B, or you can go through the region labeled C. Okay, you can either take this path or you can take this path. Okay, so this is what the symbolic automaton encodes. Now, I specifically have introduced these gray regions in this picture because these are gray regions are obstacles which we may or may not know as part of the specification, right? So this is really the model free paradigm where we don't know what exists in the world. We know parts of the world. We know where we want to go to, which waypoints we want to use, but we don't know if there will be obstacles on the way. So not everything is encoded as a specification. Okay, but part of the task objective is the specification. Yeah.
So when you compute the product MDP in the previous, don't you effectively convert your STL or the automaton?
So most of the work in the RL from TL world is on the LTL specification. So they do use Buki automata. For STL, before we started looking at, people don't really construct automata out of STL, because if you want to do everything in a principled way, you would have to construct timed automata, and that just adds a whole new dimension of complexity, right? So we are cheating a little bit. What we do is we interpret L or discrete time traces, and we basically blow up time by discretizing it. So saying reach within 10 seconds, if our time discretization delta is 0.5, we are going to say reach within 20 hops. Okay. So the symbolic automaton is somehow discretized, but it would be interesting to have these algorithms also run on timed automata. Yeah. Okay. You can also incorporate control costs in this. Yeah, I mean, we haven't, but it is possible. Like actuator and sensor bounds, for example, you can do it. You just have to figure out a way of mixing the two costs together. Yeah. Okay, so just to give you a little bit more details about how the symbolic automaton works. So the product MDP is going to start in some state S0Q0. At each step, you are going to check whether your state of the MDP satisfies the guard of the symbolic automaton. If yes, you can take that guard. And in fact, you can take it even if you don't satisfy, and then you will get a penalty for taking that edge when you don't satisfy something. Okay, and everything else kind of works out in the sense of a typical product construction, right? So all the probabilities of the original MDP then transfer over to the probabilities of the product MDP. Okay, so yeah.
Like if you have like
Yes, that's a good question. We are assuming that from the state of the MDP, I have a way to effectively evaluate the predicate that I'm interested in. Yes. Yeah, so if you want to work with images, that's exactly what you would have to do. You'll have to define a library of things where you can check for these things. Okay. So in the work that we are pursuing, there are three main ideas in this reward shaping from symbolic automata. The first idea is kind of the obvious one. Imagine an implicit product. The second idea is try to quantify how far a state in the product MDP is from an accepting state. Okay, and this is somehow related to in the imitation learning or the RL literature, they use notions of potential functions. What we define is something like a symbolic potential function. I'm going to describe what it is on the next slide. But basically, the symbolic potential function is going to incentivize moving to a state with a lower potential. Okay, so we kind of still want to keep the sparse rewards for satisfying the specification, but we want to now incentivize from each state which edge you should take, because taking this edge gets you closer to the goal. So try to take this edge because it's going to lower your potential. Okay, so the way the symbolic potential function is defined has this is the most technical part of the talk, this and the next slide. So it involves defining the symbolic subtask progress. Okay, so if you are in the accepting state, your symbolic subtask progress is 0. You're going to get a 0 for that. Otherwise, if you are in some state Q, then we want to compute what's the cost to go from Q to Q prime. Okay, the cost to the symbolic subtask progress for going from Q to Q prime is going to be what's the distance to go from Q to some next state of Q prime, let's say Q1. Okay, plus the cost to go from Q prime to Q1. Okay, and the cost of taking this pair of transitions is, if I satisfy this predicate now, how much effort would it be to satisfy the next predicate? Okay, so if I'm already in a state that satisfies the A region condition, how much more effort do I have to do to satisfy the B region condition? Okay, so you pick the minimum of these. So you are always going to try and pick the path that kind of symbolically gets you closest to your goal. Okay, so this is something you can do offline once you have your MDP and your symbolic automaton. You do this once and that's it, right? It doesn't depend on the actual current state. Yeah.
Natural indicated although that you're getting closer, but this particular path actually gets you very close, but not all the way. And then some kind of take it perfectly through the event.
I think there is an example of exactly this that I'm going to talk about in just a second. Yeah. Okay. And then the symbolic potential function is defined using this notion of symbolic subtask progress. Okay. So the symbolic potential function basically takes some minimum over all possible next states for doing the, which includes the cost of transitioning from now to the next state, plus the best symbolic cost from the next state. Okay, that's what the symbolic potential function defines. The technical details are in the paper. It's hard to kind of convey it in a small time, but that's kind of roughly the idea. Okay, the most interesting thing is that we have this theorem that shows that if you define your reward functions this way, then the optimal policy, if your RL algorithm finds the optimal policy, then with respect to the symbolic potential based functions, then it maximizes the probability of satisfying your symbolic automaton specific. Okay. So just some examples. So again, going back to this, my gripe about the RL from TL world, if you look at other methods, even after 50,000 iterations, the probability that they learn a policy that satisfies the spec is sometimes as low as 0.3, right? Whereas we are able to learn much faster and we get to probability values that are much better of satisfying the specification. In this case, we were interested in a patrolling specification. where we go to region A and then go to region B repeatedly. We have examples where we have sequential reachability. We can again learn much better than competition. And going back to Oleg's question, actually in this case, you can see in the symbolic automaton, if you take this path, there's only one hop. Whereas if you take this path, there are two hops, right? But if you take this path, you get stuck because there's an obstacle. So the symbolic potential function figures out that, actually going this way is better because going from here to here has a big penalty that's sitting somewhere in the middle. Okay, so it somehow figures out the obstacle through the way the guards are structured.
So you know exactly where they're.
No, I mean, we discover them during exploration. We don't know a priori. The potential is dynamic because, so there is a symbolic part which is computed offline, and then the final symbolic potential depends on the current state and combines it with what's computed offline. So you can think of the symbolic subtask progress something like the A-star heuristic. And then there's part which is about where am I now? Yeah. Okay. All right. So, I mean, we got some cool results with this. Just to reflect back again, it does scale for complex symbolic automata. We had automata with over hundreds of states and large discrete state action spaces. But once you go to continuous state action spaces and you have to use neural networks, things start not working well, right? So we are still kind of trying to figure out how to get it to work in those settings. We do get some guarantees on optimality convergence modulo that the RL procedure itself converges. And there are some procedures like Q-learning that have guaranteed conversion bounds, but not all RL procedures have them. So if you use an RL procedure that is not guaranteed to converge to an optimal policy, then we cannot give any guarantees. Okay. All right. Now, I just wanted to put a plug in here. We are also doing some work on learning from demonstrations, where the user gives you some demonstrations which are possibly suboptimal or unsafe, but we have an STL formula that's kind of specifying the overall task objective. And even in continuous and stochastic spaces, we can learn well. I would have loved to talk more about this, but we are almost out of time, right? So I'm going to skip talking about this. Okay. And in just 5 minutes, let me tell you a little bit about work we have been doing on statistical deterministic verification. To answer Rajiv's question, we have a neural network controller and we have a plant model. So hopefully the accuracy of the plant model, we can kind of use some machine learning techniques to reason about that, get some probabilistic guarantees. We still have to reason about the controller. So this is the verification problem. You want to make sure that for all initial states, your safety criterion when evaluated over the trajectories, it's greater than some margin, right? And if you are, the probabilistic verification problem is that the probability that you are safe is greater than some threshold that the user has provided. So for the first deterministic or non-deterministic verification problem, what we have done is we take the neural network plant, the neural network controller, and we also convert the STL specification into a neural network. Now, this might seem like completely counterintuitive, right? First of all, you have difficulty reasoning about neural networks. Now you have something symbolic and you are making it a neural network, right? But bear with me for a second, okay? So converting the STL specification to a neural network is actually not that difficult because STL quantitative semantics is a bunch of mins and maxes, which you can convert to ReLU networks rather easily, okay? So now, basically, all of the stuff that you see on this slide, except for X0 and the output of this neural network is some giant neural network, okay? So now the problem reduces to, for all X0, show that this composed feed-forward neural network operating on X0 is positive. So there are several solutions to do this, okay? One is throw an SMT solver at it. Unfortunately, it doesn't scale. If your dimension of your state space is high, SMT solvers are going to not scale. The thing that we have tried is using, there is a body of work called reachability analysis on neural networks. It's really forward image computation of the neural networks by propagating sets through the neural network. And there are robust tools like Crown, NNV, and so on that seem to work well. We used NNV for doing this verification problem. What saves us is the dimensionality of our state space. State is not that high. We have a large neural network, but NNV works, it scales. And we are able to show that for all initial states, the robustness value is positive. And the neural network encoding by STL specification is exact. It's positive only if your STL formula says. Okay. There's another solution that we have, which is sampling based, which is try to approximate the Lipschitz constant of the neural network and then do some systematic sampling. And that also scales when your state dimension is small enough. What's interesting is for this to work, your neural network needs to have all ReLU activations. For this method, your neural network can have any activation. Okay. And here's something that just shows that it's scalable. I don't want to go into the details of this. I want you to focus on this column. So the worst runtime for this problem. And here we are looking at trajectories that are 50 to 100 time steps, right? They are not tiny trajectories. And the neural networks are, so some of them are quite large, but it still seems to work. And in about less than 40 minutes, we can get a verification result out of it. Again, as I said, the elephant about is the neural network representing the plant accurate is still kind of there, but hopefully we can address that with other methods. Okay. Oh, and I just wanted to flash some specifications. Specifications are also kind of rich. Okay, they are not simple specifications. So we have quite long nested specifications for which this still works. Talk about very briefly is this is where really learning is the dominant thing that we are using, is statistical verification using this notion called conformal inference. So conformal inference or conformal predictions is a rich area by itself in machine learning. We are trying to use it for doing verification. So the general idea is as follows. So suppose you have this gigantic model, right? One end comes in the initial states. At the output, you have a trajectory, then you evaluate some robustness value, you get some value. You can think of this as a system that's generating data for you. On the input to the system is the X in your machine learning experiment. The output of the system is the Y in your machine learning, right? So you are trying to learn the black box function that maps your initial state to the robustness of the output. So you can use your favorite regression method to learn this kind of a surrogate model that approximates the effect of your system. And then once you have learned a surrogate model on some training data, you can do some quantile methods to find what's the 1 minus epsilon quantile of the distribution, the residual error of your prediction. You have a bunch of predictions that you have using your training set. On the test set, find the residual distribution on the test set. Throw that into an empirical distribution, compute the 1 minus epsilon quantile. That's going to tell you that the probability that my prediction is within with 1 minus epsilon confidence, the probability that my prediction is going to be within that 1 minus epsilon quantile of the predicted value. Okay, yeah. Exactly. Yeah, it's a difference between the predicted robustness and actual robustness. Okay, so using conformal inference, we can get this for specific points. But now the cool thing is we have this surrogate model, right? The surrogate model is going to predict the prediction intervals for each unknown point in the space. And now we can do some kind of optimization over our surrogate model, maximize what's the uncertainty, and that gives us guaranteed bounds over the entire state space. But the bounds are going to be probabilistic. With 1 minus epsilon probability, we are going to be able to conclude whether our system is safe or not. So conformal inference is a very versatile tool, right? So we have been able to use it to kind of figure out which regions of the state space are safe. So this is a complex F16 model, which has, I think, 12 or so states. And this is projected to some 2 dimensions. These are all the red regions are all the unsafe regions. So if your system starts in this state, it's highly likely that it's going to fail. But if it starts in the green regions, it's going to be safe. So yeah, it's the STL robustness. We also have a recently accepted paper where we are doing this at runtime, where we use a forecasting model to predict the trajectory in the future, use STL robustness again as a non-conformity score, and do conformal inference to give bounds. And what's the probability that in the future I'm going to violate this specification? If I know that with high probability I'm going to violate, maybe there's something I can do now before the violation happens. And also another idea which we haven't really explored is you could also use it to solve the problem you brought up, right? You can also use conformal inference to reason about how close is my plan, what kind of probabilistic guarantees do I have about my approximation of the actual dynamics with the neural network. Okay. So to conclude, I mean, is the marriage of logic and learning, will there be a happily ever after? What we have learned is that logic-based methods can improve learning-based techniques. So we can, for example, we found in our work on learning from demonstrations, it can significantly reduce sample complexity by pruning the sample space, by providing structure. It can improve explainability significantly. And most importantly, you can give some guarantees using logic-based methods, right? Whereas learning-based methods can assist in solving problems, right? For example, we can get statistical guarantees. I mean, one of the biggest open problems in verification is how do things scale? With probabilistic guarantees, we can scale to really high dimensional systems and still get something that is better than I don't know, right? So we can get statistical guarantees. This can help us increase the scalability of verification. And we can apply logic-based methods now to domains that were previously considered inaccessible, where, for example, you don't have a model of the system. How are you going to synthesize a controller? We can use kind of model-free learning-based techniques to kind of go there. And I think just a few thoughts for the future. I mean, is everything solved? Is this a happy union? I think the verdict is still out. We don't know. But I think perhaps we are in the start of a neurosymbolic era where more and more things will keep happening. This is just a very small sample of initial ideas that seem to have some promise. I think there's a lot more to be done. So some of the open problems are scalability, right? Everything curse of dimensionality gets to you. What are the kind of techniques we can look at from machine learning domain to improve scalability? Expressivity. I mean, I've been kind of trumpeting STL for a long time. I mean, you might think that I'm married to STL. My wife certainly thinks so. But, you know, I have doubts, right? I'm sure there are several tasks that you cannot express using STL, right? Especially in the robotics domain, there are several things that you want the robot to do. It's very cumbersome to express them in STL. So what are the right logics? What are the right abstractions that we can place on specifications and task objectives? Perception is, I think, one of the biggest issue when it comes to doing autonomous system design. How can we reason about robustness or multimodal perception when we have several different sensor streams? One of the other things, a whole lot of work in how do we reason about epistemic uncertainty. So we can reason very well about data sets that we have, but how can we reason about what data that we don't have? And how can we quantify what we don't know? Right? So I think here logics of knowledge can be really interesting. And we have been doing some work using some epistemic logics to kind of understand trust in autonomous systems. And I think one of the most interesting open problems for those of us who have interest in both formal methods and learning is how can we force structure on learning problems? And I think, so for example, just out of, so when I was with Rajiv as a postdoc several years ago, we were looking at learning-based methods where we were trying to learn symbolic expressions from data using various techniques. But what was powerful about that method is we could give symbolic examples. We could say something like, oh, well, if X is positive and Y is 3, the output should be Y plus 10. Right? We could say something, it's a symbolic example. It is an infinite number of examples that's captured by one symbolic expression. I don't know if we can do this with existing machine learning algorithms, and it would be very cool to be able to do this. How do we make learning algorithms respect some logical structure? There's a lot of work on using regularizers, using constraints that has been happening, but I think a general theory or framework for doing this has not really been explored and would be cool to explore. That's all I had today. Thank you so much for your attention. I know I've gone over time, but hopefully you found this interesting.